A metric space is a set, we'll call this one A, such that for any two elements in a set, x and y, we have a distance function, d of x and y, which calculates the distance between them. To produce a nonlinear space, we take a subset of a metric space that is also a vector space. Now, there are some cases where the metric space itself is a vector space. So, for example, if we have the two-dimensional plane, so the set of x and y coordinates in R², now with a suitable distance function, this could be a metric space. And it could also be a vector space because any linear combination of points within this 2D plane is also within this set. Now let's look at an example of a metric space that is not a vector space. Let's take the same set of xy in R², so in the 2D plane, but let's limit ourselves to the subset of points within the unit disk. So the set of x and y coordinates such that x² plus y² is less than or equal to 1. Now this could be a metric space with a suitable distance function, but it's not a vector space. And we can see that because we can choose a vector within this set, let's call it A, and we can apply some linear transformation, let's say multiply by the scalar factor 2, and we end up with a vector that's no longer within this set, and therefore it's not a vector space and it couldn't be a non-linear space. Now, I should point out why we're interested in subsets of metric spaces that are themselves vector spaces. Well, firstly, when we come later on to prove some properties about approximations, the fact that we're working with a vector space becomes useful in our proofs. Secondly, it's useful in a lot of real-life situations. Let's take an example from the world of data science. Imagine we have a data set where we're looking at the amount of traffic in different areas and the amount of air pollution in those areas. And this is made up data, but let's imagine that there's a linear correlation between these two variables we can model using linear regression or a line of best fit. So first thing I'm going to do is I'm going to take these data points and I'm going to put them into a table. So for every data point we have an amount of traffic, which we'll put in the X column, and an amount of air pollution that we will put in this Y column. Next, I'm going to make a third column and I'm going to call that Y hat, and this is going to contain the predictions for each amount of traffic in our X column for the amounts of air pollution in those areas. And now we're getting closer towards the reason we're interested in vector spaces. We can think of these three columns as column vectors. We're particularly interested in y and y hat, and each of these, because they have 7 elements, you can think of them as two vectors in 7-dimensional space. But we can't visualize a vector in 7-dimensional space, so I'm just going to take the first 3 elements of each of these vectors and we're going to visualize them in a 3-dimensional space. So there we have y, and here we have y hat. Y, because it's coming from experimental data, those numbers could be anything, and therefore y could theoretically be anywhere within this 3-dimensional space. Y hat, however, is constrained because that's related to the predictions from a line of best fit. And changing that line of best fit will change y hat. So for example, we could make the line of best fit steeper and that will stretch y hat. Or we could make it less steep, which will shrink y hat. We could also translate the line of best fit up and down, and this will translate y hat in the direction of the vector 1, 1, 1. Because what we're doing is adding a constant to y hat. And so the complete set of all possible y hat forms a two-dimensional vector space spanned by the vector equation y hat is equal to a constant a times the vector 1, 2, 3, which comes from our original x in our table, plus a constant b. So altogether we have a two-dimensional plane in three-dimensional space which represents the set of all possible y hat. And this is where we reach an important question. How far is our vector y from the y hat plane? This will become important when we're interested in answering the question of how good is our line of best fit. In order to quantify the distance between two vectors, this is where the concept of a norm comes in. So we're now ready to write down our definition of a normed linear space. It's a pair of objects, v and d, where v is a vector space embedded in a metric space, and d is a function which takes v cross with itself and maps it to the real numbers. So it behaves like the distance function of a metric space. We call d of x and y the norm of v, and it's usually written with two sets of vertical parallel lines. And it's useful to think of the norm of x minus y as a measure of the distance between two vectors x and y. But bear in mind that x minus y, where x and y are both vectors, is a vector in itself. And if we write down the norm of a vector on its own, for example the norm of x, we can think of that as some kind of measure of the length of that vector. Now, just like in a metric space, the norm has to satisfy four criteria in order to qualify this set as a normed linear space. So firstly, the norm of a vector must be greater than or equal to 0. Secondly, the norm of x minus y equals 0 implies that x is equal to y. Thirdly, if we multiply the vector x minus y by some constant scalar lambda, and we take the norm of that, then that's equal to the absolute value of the scalar lambda multiplied by the norm of x minus y. The fourth and final property is that the norm must satisfy the triangle inequality. So the norm of x minus z is less than or equal to the norm of x minus y plus the norm of y minus z. Let's compare the properties of the distance function of a metric space with the norm in a normed linear space. We can see at least the first two properties are identical. It's when we reach the third property where we start to see a deviation between normed linear spaces and metric spaces. In a normed linear space, we have this rule where multiplying a vector by a constant and then taking the norm of that is equal to the absolute value of that constant multiplied by the norm of the original vector. That's completely different to what's written down as the third property of the distance function of a metric space. So we have d of x and y is equal to d of y and x, which is saying that the distance between 2 points is the same regardless of whether you go from x to y or from y to x. And finally, the triangle inequality holds in both cases, so for normed linear spaces and for metric spaces. So let's take a closer look at the third property, because this is the only one that's different between our two kinds of spaces. What I want to show you is that actually these two properties are more similar than you might think. We can show that by taking the case of lambda equals minus 1. If lambda equals minus 1, then we're taking the norm of minus 1 times brackets x minus y. And minus 1 times x minus y is equal to y minus x. So we're actually taking the norm of y minus x. And by property 3 of a normed linear space, we can take that minus 1, take the absolute value of it, which gives us 1, and then just take the norm of the original vector x minus y. So we have that the norm of x minus y is equal to the norm of y minus x. And so we've changed the direction we're taking the norm, and we have equality in this case. This is exactly the same as what we see in our metric space in d of x and y equals d of y and x, except in the concept of a normed linear space, we've refined this property so that we're actually saying much more about what happens when we're performing linear transformations on the elements of our space. So let's briefly look at a couple of examples of the most common kinds of norms. Now I say briefly because we'll look at norms in a lot more detail in another video. But we'll just start off with introducing the norms L1 and L2. So we're interested in the length of a vector, x. In this case, to keep it simple, we'll look at a two-dimensional column vector x1, x2. Now, L1, which is written with these two sets of vertical parallel lines with a subscript 1, is the sum of the absolute values of the components of our vector. In this case, we only have two components, x1 and x2, and so L1 norm of x in this case is just the absolute value of x1 plus the absolute value of x2. At this point, I invite you to think about how this might satisfy the four properties of a norm of a normed linear space. The second norm I want to introduce is the L2 norm, written as these two sets of vertical parallel lines with a subscript 2, and this is defined as the square root of the sum of the squares of the components. And this probably looks familiar to you. It's often called the Euclidean distance, but we can think about it as the length of a straight line between the 2 points 0, 0 and the coordinate x1, x2 in this case. So we take x1 squared plus x2 squared and we take the square root. So just to end this one, I want to get back to our data science example of taking a set of models, in this case we had a set of straight lines, to approximate some data y. And we want to know how far y is from the plane because that's how we will find our best model to represent the data. And so using our concept of a norm, we can now see that finding the line of best fit is equivalent to finding the vector in our set y hat, which minimizes the norm of y minus y hat. And you can imagine how using different norms might lead to slightly different models with slightly different properties. So in the next video, we'll look at norms in a lot more detail.